Hello, and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. In this podcast, the audio is from a conference I spoke at. It was a really good conference, very interesting. It was called the Integer Emissions Summit, and that was held in Dresden in Germany in June 2017. It's still very relevant today. I spoke about the opportunities for electrification in heavy-duty machinery, and in particular I went into some depth about our experiences with 48-volt mild hybrid systems and 24-volt micro hybrid systems for off-highway and commercial vehicle applications. So I really hope you enjoy the podcast, and let's get on with it. Morning, everyone. So just in case you don't know who Avid are, because we are a fairly small business, we are based in the northeast of England, so just north of Newcastle, and we've been involved in electrification of vehicles since the beginning. So it's fair to say since before it was fashionable, and it's very much become fashionable now. Our particular expertise is around the ancillary systems on the powertrain. And the core competency of the business is really very high power density electronics and motor design. And really all we do is heavy duty and high performance vehicles. Often, unfortunately I don't get to drive many cars with our stuff in because they're made by companies like McLaren and Koenigsegg, and I can't afford them. So just a bit of general background. We see three trends in the marketplace that are kind of driving activity within our customers. The first sort of big one is clean air. Really, you could argue the climate change element, but in the last couple of years, the clean air agenda has really come to the forefront. And that's definitely been helped by the Dieselgate scandal that's been mentioned a few times already in the last couple of days. But we're really seeing that drive a huge amount of activity in our customer base, developing solutions which are going to be compatible with the sort of the clean air demands and regulations that are coming for cities. So I know it was mentioned earlier about clean air is important in non-urban environments as well, but really we see that being the drive. And I wouldn't say, because money is always a problem, but it's definitely the driver for this is not cost. So some very different conversations with machine manufacturers who, normally it's all about the added cost to the machine and the return on the benefit to the operator. This is basically just, about getting product that's zero emission capable, that can operate in cities. So there's some examples there of buses and cars and trucks, which truck particularly mentioned already this morning. But we're also seeing this in construction machinery as well. So the other interesting trend is electrification for performance. So this is kind of right at the opposite extreme. There's an interesting kind of thing that's really come through here in terms of an angle on electrification of the vehicle powertrain. So probably the neatest example on there is the Koenigsegg, which is an absolutely phenomenal car. So huge engine, but actually enormous electric powertrain in that vehicle. The McLaren P1 has some criticism for being hard to drive because it's too quick. The Koenigsegg must be almost impossible. But the story from the manufacturer is around their experience in the past of developing a very high performance internal combustion engine powertrain. And what they found is actually they can deliver a much lower platform engineering cost to go with a very high performance powertrain using the electrical solution, so hybrid solution. So McLaren currently only have a P1, which is a hybrid. Again, they learned from that experience. This electrification can allow us to extend the performance of a base ICE engine. So now the new McLaren strategy, which has been announced, all of their vehicles are going to be hybrids. So they're basically going to standardize on one base engine and then fill in the performance gaps with electrification. So these are all kind of really neat examples from the passenger car world. And I can say there are clear examples that we're working with customers in the commercial vehicle and off-highway world, where you might at the moment use 4 or 5 different base engines, but using a smart hybridization strategy, you can standardize down onto one engine and then fill in the performance gaps with electrification. So the piece part cost on the machine is likely to be slightly higher, but the platform engineering cost is likely to be much lower. So if you're only selling quantities of hundreds or low thousands of vehicles or machines, then actually that can have a significant impact on the cost of the machine. So it's an interesting example. Obviously some pretty pictures, but it's basically, it's not always about the platform, about the component cost. And one other interesting thing that's happening at the moment that we can see with the likes of Tesla, Lucid, Faraday Future is this sort of rise of some new car manufacturers. And the simple reason for that is it's now very possible to develop a vehicle with an electric powertrain for a much lower entry cost than an ICE powertrain. So I think we'll see some more of that in the future and some big changes. So this is interesting, obviously interesting in passenger car, but has some real practical applications in commercial vehicles and off-highway. So the final trend is the slide says CO2, but actually really it's fuel saving. So unfortunately I've learned the hard way that customers are not particularly concerned with the environment unless there's some sort of net benefit in operating costs to the vehicles or machinery for them. So we do see a lot of activity, and in fact Avid's core business really is this electrification for fuel saving. So that's been forced in that over the last 10 years we've had a clear agenda as a business, but convincing customers that it's worth investing in powertrain electrification has meant being very clear about what the benefit is in terms of a fuel saving and a payback versus an add-on cost to the vehicle. So there's some nice examples there. The micro-hybrid bus system, so basically now in the UK and in North America, pretty much 100% of new buses sold are what we would class as a micro-hybrid. So they have a 24-volt base electrical system. They use a smart charging system, so it's a controlled alternator to basically turns the alternator off when the vehicle's accelerating and turns it on when the vehicle's decelerating. So you're only generating electrical power under braking, so regen braking effectively, albeit at a fairly small scale. And then there are other components electrified on the bus, and depending on whose bus it is, the extent of electrification varies, but the absolute base is electrified cooling system, so replacing the hydraulic fan drive with electric fans, and then the add-ons are electric drives for power steering pumps, electric drives for the air compressor, and the other ancillaries on the vehicle. And the bus market's really shown, it's an interesting example where normally when we're talking about electrification, it's all about traction. So we're thinking about, do we replace a diesel engine with an electric motor to propel the vehicle? But actually in particularly buses and off-highway machinery where it's highly transient operation and there's very high parasitic loads on the engine compared to the engine power. So things like the cooling system will be taking a huge amount of power out of the driveline relative to the engine power, especially compared to a passenger car. So there's a lot of potential there. Obviously, there's a lot of product launches happening now and coming through with the low voltage hybrids in passenger vehicles, so 48 volts is the new standard there. And the nice kind of real simple explanation for that is it's the 80-20 rule. So and I've seen loads and loads of people present on 48 volt hybrids and they all come out with the same conclusion. You get 80% of the benefits that you do with a conventional high voltage hybrid for 20% of the costs. Okay, so if you're in a market where you don't have to be able to demonstrate zero emission running for the vehicle, because actually sometimes you do. So some of the regulations around hybrid buses, for example, in different countries and cities require a certain amount of zero emission running. But you don't have to be able to demonstrate that. Actually, the 48 volt mild hybrid in passenger vehicle is a very good solution. And then also the other kind of market which is often overlooked is the light and medium duty commercial vehicles. So we see a lot of potential there, particularly because it's all about operating costs. So in a lot of ways in that market, almost the purchase price of the vehicle isn't really a factor. It's about fuel consumption and driver utilization and operations. It's all about the total cost of ownership. So this is an area that we've kind of made our speciality. This presentation now gets very off-highway, and that's because of the connection with Caterpillar. So we have a program with Caterpillar which is partly funded by the UK government, which is looking at the opportunities for cost-effective electrification on off-highway machinery. So we just pulled this slide out in terms of, okay, if we think beyond the basic traction system on a typical machine, so this is a wheeled loading shovel, but it could be any machine, and there's another example coming up. What are the kind of main things that we could electrify without looking at the base engine? So you typically got big parasitic loads coming from the cooling system, from the fan, because off-highway machinery doesn't move very fast. By its nature, it's operating in dirty environments. Cooling fans are normally specified in such a way that they give full cooling airflow at 0 vehicle speed. So normal kind of rule of thumb will be somewhere between 10 and 20% of the engine power will be going just to drive the cooling fan. You'll also have typically a cooler in that cooling pack just for the hydraulic drive for the cooling fan, so the sort of fan's cooling itself, which is slightly strange. Next on, we've got the HVAC systems. So again, in off-highway machinery, because of the demands for health and safety for the operators of the machines, there's huge power consumption from the ventilation and air conditioning system, air cleaning for the cabin. So there tends to be a lot of parasitic power consumption from that system. We also have, this is a wheeled loading shovel, so articulated machine, has a separate steering pump, so there's a hydraulic pump in that machine for the steering drive. Crank assist alternator, and then obviously the engine coolant pump as well. So all of those things are quite easy to implement at a machine level, other than the engine coolant pump. We're obviously in low volume machinery, and even a big corporation, effectively the machine groups have some degree of separation from the engine group. So effectively, even though it's an internal customer, it's still a third-party customer. So making changes to the base engine are quite difficult, but are starting to happen. It was interesting in a presentation yesterday, which was actually by the guys from JCB looking at the NOx emissions. It identified the initial part of the drive cycle during the engine warm-up period as being sort of the next kind of big win. We are seeing, not just with Caterpillar, but a lot of activity around the engine coolant pump based on that. Because obviously if you can control the pump and decouple it from the engine speed, you can increase the engine warm-up time significantly compared to a standard mechanical pump. To us, electrification like this always seems like a bit of a no-brainer. And to be fair, we get a lot of objections, so we get used to this. And even within customers where we have running programs and proven product, you still come across people who are naysayers and they don't quite get it. So when we're looking at taking the belt drive loads or the feed loads off the engine and electrifying them, there's always typically an objection that it can't be as efficient. So if we're driving something mechanically off the engine, there's only the belt losses. It's pretty much nearly 100% efficient in terms of the drive. If you want to now make that electrical, we've got the conversion losses of going from the engine to an alternator to a battery and then back out to the device. So there's no way it can be as efficient. So that's normally the first and biggest objection. The other problem that we've come across a lot now is to do with simulation. So really the electrified components, particularly on the ancillary systems, come into their own under transient operation. But basically all of the modeling tools that are currently used don't accurately model transient conditions. So the big sort of software packages like GT and then the internal OEM packages, they're multi-steady state point operating conditions. So it's very hard in the normal sort of design process of, okay, we'll do a simulation. The results you get out of the simulation don't tend to make any sense. So we see a lot of issues around simulating effectively transient operation of these electrified systems. So there's a lot of work's gone into that. The other big problem is electrical power. In buses, we're quite lucky now that
Globally, 24 volts is a standard. It didn't used to be in America. They used to run 12 volts on very big buses. So there's a lot you can do at 24 volts. In off-highway, quite a lot of the machines are 12 volts, base electrical architecture. So that is a limiting consideration. So there are some really, really straightforward things. So 24 volt base machines that you can do, very, very cost effective, sometimes even cost saving compared to implementing hydraulic drives for ancillary systems. But there's always a big debate around electrical power. How do we upgrade the electrical systems? What do we have to do for energy storage? Not enough electrical power is available. And the final one is about customers not being willing to pay the additional cost. So everyone is very conscious about adding cost onto machines and vehicles, and basically looking at an up cost scenario is very difficult to get that through at a senior level within any OEM. And it doesn't matter who it is. You know, if you're going to the board and saying, we want to implement this new technology and it's going to add $100, $1,000, whatever it is to the cost of the machine, you're going to get quite a lot of resistance. So being able to understand the economics and the market in terms of are the customers willing to pay for this is really important. On that final one, I can address that point before I move on. So we actually took this to the OEM market 10 years ago, and to be honest, we weren't very successful. We were talking to people about electrification and getting laughed at and thrown out of rooms, and it was like, I'll make a film about it one day. It'd be quite funny. Actually, we established an aftermarket business unit, and we now have a small team in the UK, quite a big team in North America, where we retrofit low voltage micro-hybrid systems to commercial vehicles and off-highway equipment. And it's quite expensive to do that because we're going out, we've got to have field service guys who can go out, but the economics, even at that level, make sense. So when it's an OEM fit, it can make even more sense. One of our better customers in the UK is a bus manufacturer called Wrightbus. They market their micro-hybrid thing as an actual, as a tag on the vehicles. So they add a premium to the cost of the vehicles, and actually the best margin they generate on their bus sales is through the additional margin on the micro-hybrid system. It's a much better margin than they do on a flat bus sale. As of this year, 100% of the buses that Wrightbus sell are now micro-hybrid buses, and they've got 3 different levels of micro-hybrid. So kind of the market, if you can demonstrate a cost saving to the end customer, the customers are smart enough that they know it's not just about the purchase price of the vehicle or the machine, it is about the total cost of ownership. So this is kind of going back to the first point, so to do with the efficiency. So what we find, we've got 2 example driving cycles. So interesting, we've been talking a lot about driving cycles the last couple of days. So the NRTC and the WHTC there, they're basically very, very transient. So off-highway machines, buses, anything operating in an urban environment has exceptionally transient driving conditions, stop, start, accelerate, decelerate, on the power, off the power. When we look at the efficiency of a typical ancillary, so in this case the graph shows a fan, so this would be an engine-driven fan. Obviously, it has a peak efficiency, so actually fans are not very efficient generally, so 25-30% efficiency is good for a fan, but it falls off very sharply as soon as you're out of that peak operating point. So as long as your pump and your fan and all your other bits and pieces are attached to the engine, they're being dragged around doing what the engine wants to do from a speed point of view. So actually, whatever you've gained in terms of belt efficiency, you've lost in terms of those devices being off their peak operating point. And what we tend to find is that, so particularly the cooling system components, will be specified for the peak torque, peak engine power output operating point, which basically the vehicle spends almost no time sitting at. So it might be 80% all the time, or constant speed, variable power. Those applications are really interesting. So things like excavators, where you're running all the ancillaries at constant engine speed, but actually the load on the engine is varying up and down. So there's a huge kind of under the curve performance benefit that can be gained, and that's without even considering the smart charging. What we've found in the work that we've done in off-highway on different machines and also on-highway is that it's possible to recover all of the energy required to run the ancillary systems on the vehicles and machines under the braking, so through regen braking on the machine. And even when we're doing a 24 volt base system, we don't have to go to a fancy lithium battery pack. We just base, good quality lead acid batteries. They work as a good energy store, and we can get all of the power that we need for the ancillary systems essentially for free from a fuel point of view. So we're just charging under braking, and there's a lot of off-highway drive cycles that are the same as that. Not all of them. I think the most difficult one was mentioned yesterday, which is the dozer, so the track-type tractor. There is no regen braking potential in that drive cycle at all. But in pretty much all the rest of them, there is some element of recovery possible. So the basic benefits that we're getting there, we can help at real world performance level because we're decoupling these components now from the engine speed, and that's so all the sort of hydraulic drives and the accessories that are sitting on the engine. So we basically can optimize the component design. So what we don't do is take an engine-driven fan, stick an electric motor on it, and hope for the best. That doesn't work. So we optimize the components, we optimize the pumps. We move the best efficiency point on the pump so that it reflects where the pump is actually spending all of its time operating. So we still have a sort of peak operating point, but actually the best efficiency point will more accurately represent where the pump is going to sit now. We can support stop-start. So one of the things that has been found in the bus industry, that has been one of the first heavy-duty markets to adopt stop-start engine technology. If you have a hydraulically driven steering system with a hydraulic pump which is connected to the engine, and you stop the engine and you've got a bit of steering lock on, the steering wheel quite violently kicks back. So that's not very good. Drivers don't like that. It's a safety concern there. So basically you have to have an electric hydraulic pump to facilitate stop-start engine operation. But then when we've peeled off the other parasitic loads from the engine, what we've done is reduce the cranking load on the engine by over 60%. So actually, if you've got a stop-start engine, one of the limitations tends to be the life of the starter motor. The life of the starter motor is a function of how many stop-start events you want to have per hour and the cranking load that you're putting on it. Taking all these parasitic loads off the engine takes that load off the starter motor. So you can have better utilization, you can enable more start-stop events per hour with electrified ancillary package. We've got a pretty cool video of two buses drag racing. So that's what we do for fun in Newcastle. It's moved on from burning cars and barbecuing things. So in the drag race scenario, it was the difference is huge between a very simple electrified ancillary bus and a standard bus. So you don't often want your buses and off-highway machines to drag race, but it's a very kind of good point about that low speed power and the power consumption of these devices at low engine operating speeds. So the third kind of big instrument, and where we have a lot of interest now, and I think that's sort of based on what was said yesterday makes sense in terms of the thermal management. So if you want your SCR to work properly, you want your DPF to work properly, your engine has to be at the right temperature. Basically, it's quite hard to get a modern diesel engine up to the right temperature under normal operating conditions. So there's loads of issues with low temperature operation. I heard last year about a fleet of excavators that an end user had purchased and then returned because he was unhappy with the number of regen events that were happening. Sort of every couple of hours, these excavators were going into regen, basically because they were cold. The engines are not getting up to the right temperature. And we find that a lot, but through electrification, we can improve that thermal management. We can improve the efficacy of the after-treatment system. There is a safety angle, not so much in off-highway, but strangely in the bus industry, there's a bit of a thing with buses going on fire. In North America, this was a huge problem. The hydraulic drive systems, essentially, that are used for the cooling fans, very prone to leaks, and that hydraulic fluid is then incredibly combustible. I think off-highway equipment tends to be designed, the off-highway guys are hydraulic people, so there's a different kind of design standard there, but big issue in the bus industry with bus fires to do with hydraulic system leaks. So there's a safety angle as well. And the kind of final thing actually is other technologies. So it's been mentioned about waste heat recovery a couple of times. We have the possibility with 48 volt systems particularly to implement waste heat recovery, so ORC technology, but also thermoelectric technology at 48 volts. Electric superchargers, turbochargers, which are known to be a good tool to improve transient engine performance and emissions control. Basically, you can't make a 12-volt electric turbocharger that's very effective. You're speed limited on the machine. So 48 volts, now that starts to happen. And the other big thing is actually my friends at Koenigsegg have been quite big on this one, is electronic valve actuation. So they're always one of those dreams that certainly I used to have, being involved in engine development, was being able to actuate the valves electronically and get rid of the cams. Very, very hard to do that at 12 volts, like impossible. 24 volts, very difficult. 48 volts, actually very feasible to do electronic valve actuation. So it's a real enabler for other technologies, just putting a decent electrical system on. So onto the Caterpillar story. So we got to know Caterpillar through this project. So the famous rigid frame mining truck. This is it was an aftermarket project. The people at Caterpillar found out about it, and then we ended up working with them on something more serious. So this is a huge truck, massive engine, 1,000 kilowatts plus, I think maybe 1,100 kilowatts rated power. We implemented a 24 volt micro hybrid system on this. So we basically electrified the cooling pack, put a smart alternator on it. And actually this delivered 15% fuel saving. So this truck uses something like 90 litres of fuel an hour. So 15% fuel saving is huge in terms of the operation of the truck. So it was quite an interesting project, developed a lot of interest, and particularly with CAT, and then led on to a much closer relationship with them. So we've been working now with CAT for a couple of years on the UK-funded project, Innovate UK. And the topic of that program is really two areas. It's waste heat recovery and electrified ancillary systems. So the waste heat recovery part, I think, is fair to say that's probably more at sort of proof of concept, initial low TRL level stage. The electrified ancillaries, though, actually have been very, very successful, gaining good traction in terms of what we can do with those parts. So looking at something like the articulated truck system around the base engine. So there is a very advanced control system. We've got a very smart crank assist generator on there, so that is controlled based on what the vehicle is doing, based on what the battery state of charge is. It's very power dense, so we're getting close to 20 kilowatts out of that machine. Electrified cooling system, electrified pumps, so there are some other electrified components on there. But getting some really good cost-effective savings on that truck, that driving cycle. So an example of what we've done. So essentially this had a very classic cooling system design on this truck, a large hydraulic fan, radiator, hydraulic oil cooler. It's a little bit unusual on the articulated truck. They've got two cooling packs. There's one at the front and one at the back. The reason for that historically was because of visibility regulations. So they've got to have a tapered nose on the vehicle to have driver visibility into the right areas. So they didn't have the frontal space at the front of the vehicle to have a cooling pack. So they'd already split the cooling pack out on the machine. So they have some of the cooler group at the front, some at the back. So essentially, working with almost standard cooler group, we've taken off the hydraulically driven system and we've gone to an e-fan system. So I mentioned before about the hydraulic oil cooler. So this machine does have a hydraulic oil cooler, which is just for the hydraulic oil of the fan system. So obviously we can delete that. So there's a cooler saving there. And we've used a fan array. So a fan array is a bit counterintuitive. Most people say, well, okay, fan laws tell me that a big fan is more efficient than a little fan, and that is true, to move a given amount of air, but lots of little fans are more efficient than one big fan to move the same given amount of air when you go through it from first principles. So our preferred approach is always for an array of fans that we can control, and we control those based on the temperature requirements in the different cooling groups. So it's very important that we've got split cooling packs on this. So we've got fans running just on the charge air system. We can control that independently of the jacket water temperature on the radiator, and always running with an array of fans. We have a large fan and a small fan, and we mix and match those up to get the best coverage. With smaller diameter electric fans, we can actually mount those much closer to the heat exchangers. We are able to eliminate a lot of the built-in losses in the vehicle design. So essentially, there's always a fudge factor when you're designing a cooling pack that says, okay, that's my fan performance, that's my airflow performance for my heat exchanger, and now it doesn't work on the machine, so I've got a difference between the two. That's my built-in resistance value for the machine, which is partly a function of the grill, that the air has to be drawn through, but also partly a function of just ducting losses and the fan loss between the heat exchanger and the fan. So a large fan, you have to accommodate for the fan blades flexing and moving around, particularly an engine-driven one, even on hydraulic. So you can't mount it very close to the heat exchanger. It has to stand off by quite a long way. We get a lot of loss in that duct because of that spacing and the ducting losses. We call them ducting losses. So actually, our electric fan system, in pretty much every case, is less than 20% of the power consumption of the hydraulic system that we've taken out, and that's on medium trucks, articulated, heavy off-highway machines, wheeled loading shovels, buses, etc. So there's a big, just simple parasitic power saving by going to electrified devices. And again, that's without taking into consideration the fact we can get our power for free under vehicle braking. So it's what we did with the cooling group. So this slide is now, again, a cat went crazy, and they took off the scales on the axes and the kind of interesting bits of information. So it's quite hard to understand what this slide means, and I do apologize for that. Basically, what we found, we've done a lot of modeling, we've done a lot of machine testing, we've done a lot of dyno testing of the components, the system, everything working together. We got something like just on the coolant pump, something like an 80% power saving in the power consumption of the cooling pump by going to an electrified pump. We're able to hold the engine temperatures much more stably. So the top graph here is engine temperature. The blue lines are the standard truck, and the green lines are the electrified truck. So you can see the engine temperature is much more consistent across this particular driving cycle and all the driving cycles. So it's been very effective in terms of the thermal management for the engine. It's very good. Direct power saving on the parasitic loads of the components, and able to target the cooler groups particularly. So there is some issues on, so if you do on-highway truck design and you've got a conventional cooling pack on that, there's a lot of problems with things like thermal shock, temperature cycling in the cooling system. And essentially, thermal shock is a function of the coolant in the radiator being kind of overcooled by the airflow, because normally you're running that fan because you need the charge air cooler to be cooled, not the jacket water system. Your thermostat cracks open a little bit, you dose the engine with cold water, thermostat snaps shut, cycle repeats, and we've got a lovely little animation of that happening on our website. So actually taking out thermal shock, thermal stress, that's got some big advantages for reliability, but to the extent where we saw a reduction of a factor of 1,000 in thermal shocks on the engine. So now we're looking at, well, actually, can we downgrade the spec on the heat exchangers? Because we don't have to be able to do 500,000 thermal shocks anymore. So there's some other kind of benefits coming through there. So this is particularly just looking at the engine cooling pump, and I mentioned we had an 80% power saving. So on this program, on the articulated truck, across the full range of drive cycles that CAT used to validate machine performance, we're seeing more than 10% fuel savings on all those driving cycles. The system, it does have a lithium battery, so it does require a 48-volt battery. It's not a very big one. It's only 2 kilowatt hours, so a very small battery pack needed to make this work properly, and really delivering quite a worthwhile fuel saving. So in terms of what the operator of that machine is going to save, there's a clear and fast payback in terms of the up cost on the machine, because there is, in this case, an up cost on the machine. We could have not gone for 48 volts and done simpler electrification. So it was possible. This was a 24 volt base machine. We could have electrified some of the components, but not all of them. We had about 6% fuel saving with that approach, but it was decided to go with this approach because it gives an architecture then that is flexible, that can do more in the future in terms of adding other features and taking things away. So there was a very kind of clear business decision, lots of analysis, lots of sort of big sessions in deciding on the pathway, and do we stick at 24, do we add the 48, is it worth it, the extra cost of the battery being significant. The thing that really helped us in that discussion was even during the time period of this project, the cost of that battery halved. So now actually it's it's not actually that expensive to implement a 2 kilowatt hour high power battery that you can use for this kind of thing. So there we go. So the summary is there's some significant benefits through electrification. It is a mega trend. Not everywhere, some manufacturers you go and talk to and they're kind of not really looking at electrification yet. We see huge amount of activity, and really at Avid, I can say that we've gone from sort of selling the concept to people 5 years ago to now delivering programs and having things in series production. Where a full EV isn't practical, so we've talked about lots of examples the last couple of days with long haul trucks, off highway machines. Actually, there's still a lot you can do through low voltage, mild and micro hybrid systems. And there's also a really good angle on that just from diesel engines have got a bit of a bad reputation, but there's a sort of badging, marketing angle on this as well, that you can actually add some value to the machine, add a premium to the machine as well. The RDE certification particularly, so this is passenger car orientated, basically is pushing a huge amount of electrification. So one of the things we've seen a massive surge in is passenger car electric coolant pump demand. So that was something that was kind of a fringe activity. BMW did it, a couple of others did a little bit of it. The last 12 months, we've probably had more inquiries for electric coolant pumps for passenger car engines than we have in the last 10 years. And a number of programs now moving through to production. Same thing for the heavy engines as well, with the coolant pump. The 48 volt system does have some advantages. The big disadvantage is it does add another level of cost and a 48 volt battery pack. So you're going to have to put a lithium pack on it. It doesn't have to be that much extra cost, but there are some significant benefits that can come through that. And one of the other sort of key points that's come out recently for this is that it's not necessarily a choice of if I do that, I can't do that. So on high voltage EV or HEV, typically the biggest power consuming devices on that vehicle will be the pumps for the coolant, the fans for the cooling system, the power steering drives. And actually, if you're running all of those at 12 or 24 volts, there's some good benefit on a high voltage EV of going to 48 volts. And the cost of a 48 volt drive for something like a power steering system is significantly less than a 600 volt drive. So actually, as a sort of 3 voltage architecture, there's a lot of people, not for series production yet, but working on that in terms of a concept to take cost out and put improved functionality in. So if you've done the homework and you've got a 48 volt system developed already, actually it's not sort of exclusive. You can use a lot of that equipment on your full EV or HEV powertrain to improve the parasitic losses. Even just things like reducing the size of the cabling. So you go, for a 5 kilowatt electric machine on a 12 volt system, your cable's the size of your arm down to 48 volts. So you can take weight out of the machine or the vehicle as well through that. So there's a lot of benefits that can come through some fairly simple electrification, and it doesn't always have to be about the primary drivetrain. Electrifying the components around the engine allows you to keep the basic the benefits of the diesel engine and the range that gives you, but deliver still CO2 savings and emission savings, particularly through the thermal management angle. Okay, thank you.
Okay, thank you. So thanks for the presentation. It's recognizable that you're really deep into that stuff. Who has questions on that? And certainly I have a question. John Deere, as the largest agricultural equipment manufacturer, they did the auxiliary electrification in 2007. They showed it on the Agritechnica fair.
Yeah.
And they have taken it out somewhere around 2010, so it's not on the vehicle anymore. It's not in production. And they found they had the same reasoning why auxiliary electrification makes a lot of sense, and they don't have it in it anymore. Do you have any explanation for that? Do you know about that?
I believe that the auxiliaries, that was the concept, or the kind of electrified back end system. So the putting electrified devices on the vehicle. There's I think work still going on looking at the on-engine devices, so improving cooling system, pumps, etc., and a lot of work on hybrids. And they're not alone through that. So, but I think the particular problem that in the past was just that the market wasn't there for the accessories, so you couldn't buy a seed drill that was compatible at the right sort of price with that system at that time. So they may be a little bit too early back then.
The component availability.
Yeah. Whereas now, actually, that's changing, and the back end electrification, there's more manufacturers who are doing that kind of thing. So more components.
Yeah, and talking about the electrification, we are in the midst of the hype cycle. We had the hype of electrification in agriculture in 2010, 2011, and now we are in a deep valley. Most of them have at least reduced a lot their electrification work. Everybody is waking. So at the moment, agriculture business is thinking about do we electrify our drivetrains, and if we do at all, when is the time to do it? And it doesn't seem to be at the moment.
Yeah, so there's for agricultural machines, I think it probably comes back to what I was saying before about it's easy to get carried away on the traction system. So everyone thinks, electrification, that means traction drive. That's it, end of story. I can say that I'm aware of a lot of agricultural vehicle manufacturers who are still very, very engaged with electrification and with products coming into series production in very near future, where it's highly electrified drivetrain, but not a sort of classic high voltage EV or HEV system. So there's still a lot coming through there, because the fundamental problem is actually packaging a battery pack into a tractor that's big enough to do a day's work is almost impossible. So you've then got to be a hybrid, and then you've got with a hybrid system, you've got packaging issues and cost issues, because you've still got the cost of an engine, you've got an expensive drivetrain. So the economics of a high voltage hybrid in that market don't work at the moment.
Mm-hmm.
But the economics of the low voltage, mild, micro hybrid systems on this kind of equipment do really work. The one, I think, in agricultural equipment, it's very different to things like construction machinery, and actually to particularly the bus market, where normal buses do maybe 16 to 20 hours a day, 360 days a year, with a couple of days off for good behaviour. Agricultural machinery tends to be a bit more application specific, less highly utilised, although that is changing. The usage model industry is changing. So the sort of cost savings you can get from a high voltage hybrid in some applications, where it is like the fuel saving pays for the extra equipment, doesn't necessarily translate through into the volume agricultural applications. But in some places it does make perfect sense.
Okay. So that's all for today. Thanks very much for listening. Please don't forget to subscribe to the channel. Leave us a rating or hit like, depending on which platform you're listening on. It really helps us to reach more people and get the message about vehicle electrification out there. So thanks very much, and look forward to talking to you again soon.